Okay, so we're back. I've gone ahead and cleaned up a few things and committed my files, and I've also gone ahead and added a background and a border to this canvas to make it a little bit easier to tell where the canvas starts and ends. And if I click and focus the canvas, the border turns black, and if I click away, then the border turns gray. So it's also easier to tell whether or not the canvas has been focused or not. Now the next thing we're gonna do here is we're gonna pin some joints so our system doesn't just continue to fall through the floor. So I'm gonna add a third parameter in the constructor here to determine if it's been pinned. And that means that it will not fall. It's basically just pinned to this canvas. Like if it was literally like a piece of paper, it's just pinned to it. What I have here is in the constructor, I've determined if this joint is pinned or not. If it is pinned, we just skip the motion computation, and we also fill the circle in black. So in here, I'm going to set one of these to pinned and the other one not to pinned. And now when I refresh, I should see a visual difference, and the simulation should also run differently. And it definitely did. So it looks like the forces on the spring could be swapped. So let me go ahead into the link class here, and I'm going to change this to a positive and this one to a negative. And I'm going to rerun that and see if it fixed it. This will be another debug session. So it seems like it's working a bit better now. So I actually switched this back and put the force on joint 1 to be negative and the force on joint 2 to be positive. But the one thing I did change here was that I added this reset forces function to set the forces on joint back to 0. And this is something that we could do every frame. So we reset the forces before we apply gravity and the forces from the internal system. And then after all the forces have been, well, we reset and then we apply everything. And then after that, that's when we can compute motion. So this is what I expected, but for some reason, it's just really slow, and I have no idea why. I actually have a theory. I think it's because since I'm sort of doing this in the metric system, where I'm assuming like time is in seconds, so I divided by 1000 here, I also assume like this 9.81 is meters per second squared. So that is, so I'm assuming length is in meters. So if length is in meters and time is in seconds, I could be assuming that mass is in kilograms. So we're just assuming that force is in newtons. So we're basically using the metric system here. And so that means my distance unit, like I said here, is meters. So how I'm doing the computation here is that my distance unit is actually in pixels and not meters. So what I need to do is have a conversion factor in between pixels and meters, so it actually looks like a more realistic system. So I could add another scaling factor here, for instance. So if I said, so let me create, I'm gonna just rip it out and create a new file called globals, and I'll put that over here, and I will say pixels per meter, and I'll say 10, just to try something. I'll export that. So if my pixels per meter is 10, that means every time I compute a position, I need to scale that by a factor of 10. So I'm going to import that and use that constant. And now when I refresh, I should expect it to move a little faster. And it does. So I can actually increase this a little more, let's say like 50, and refresh that. And there we go. Now we get a bit more of a realistic motion here. So far, this is actually all going pretty well. I did have a few of those hiccups, but we were able to solve them. So you need to reset the forces on every loop. Otherwise, you're just adding more forces on top of the ones that you'd already added in the previous frame. And so it just gets chaotic pretty quickly. So that's one of the things. You can add pinned joints to add non-moving ones. So to see how this is fixed in motion. It's also important to add a pixel per meter conversion here too. And now, since I have this globals file, I'm actually going to rip out some of the other constants that I have here. So I'm going to create one for gravity. I will create just a length factor here for my line width and my radius for the joints. So now I have this globals file where I can tweak the different constants here. So at this point, we can start adding more links and joints just to see how the system behaves. But before I do that, I'm going to go ahead and commit everything. So now I'm just going to build that simple truss that I had drawn up in the previous video, and we're just going to simulate it. All right, so what I've done here, just for to make things a little easier, I've actually converted each individual joint variable into an array of joints, and then I did the same thing with links. So in my loop function, I can iterate through each joint, reset the forces, and apply a gravity, and then do the same thing for links, and then compute the motion after everything has been applied. Then I can also iterate through each link and joint to draw them as well. So let's try to simulate that and see if it works. All right, so I think this will do it. So let's refresh, and there we go. I mean, I saw it for a second, and then all of a sudden it just completely exploded. So basically, each one of these joints, I set a mass of 1, and I set a stiffness factor of 100 for each one of the links. So if I decrease that, for example, if I just set each one of these to 1, and I run that, since it's a little bit more stretchy, it doesn't vibrate as much, and instead it will have this smoother motion. See, look what happens when I increase that by a factor of 10. You'll see that it looks a lot more stiff and it's going to shake around a bit more. So I believe what happened when I set it to 100, the little vibrations were kind of overcompensating due to just rounding errors in the math. And eventually it vibrated so much that it just kind of exploded. So I think that's why. And I have an idea how to fix this. So we can also introduce the idea of damping. And so I'm going to pull up my drawing tablet one more time and show the equations for that. Okay, so a standard equation for damping is just the force is equal to a damping ratio times the velocity of an object. So for example, if I have an object that's moving in this direction with this velocity, so actually there should be a negative in here. So if I have an object moving at this velocity through some kind of fluid, I'm going to have a counteracting force in this direction, assuming that there's a damping ratio of this variable b here. So it's always in the opposite direction of the velocity. So if we add some damping into our linkages, we shouldn't see those vibrations that increase to infinity. So let's give that a try and see if it works. So that's going to go into the joint class, into the compute motion. So since we don't store the velocity, we actually store the momentum, which is mass times velocity. We're going to have to divide out mass again into our calculation. I will change this to apply gravity and damping. So we have an applied force here. So we're going to do that again. I've applied a force that's proportional to the momentum over mass, which we know is velocity. And I've scaled that by some damping constant, which I haven't defined yet. But I just wanted to show you like this, so I can actually combine these two scale bys, if I wanted to just do scale by damping over mass. So now I've applied, so I have gravity up here, and I've applied the force of damping. And so I added a negative sign here too. Now that we have that, I'm going to go back into my index file and change this apply gravity to apply gravity and damping. And so now, even with this extremely high stiffness that's making it vibrate, the damping should calm down the system and make it settle into a steady state. So let's give that a try and see if it worked. So it didn't, but I can also try to increase the damping to see if it's just because I didn't damp it enough. I'm going to set these back down to 10. I'm going to increase the damping just to see if it actually does what we expected it to do. So when I have a damping factor of 100, the system doesn't even move at all, really. If I have a damping factor of 0.1, we can see that it moves a little bit. So the damping factor is working. So for now, we're just going to leave this at a stiffness of 10. So there's two more things I want to wrap up in this video. Just to make the simulation a little bit nicer to build and deal with, I'm actually going to create a new class called structure. So this structure is basically going to take in an array of joints and links, and it's going to run the simulation on its own. And so I'm just going to basically copy this loop code, and I'm going to paste it into the structure. I'm actually going to separate these functions. So now that I've set up this class, I can create a new structure in here. And then I can clear my canvas and then draw the struct. So I should expect to see the exact same thing because I just copied it over to a new file. So let's run that. So it works. And now the last thing I want to do here is add the ability to apply external forces. So here I'm going to allow just for one external force just to start with. So we're going to apply a force as a vec3, and then we're also going to select which joint it's applied to. So in this step function right here, before we compute the motion, but after applying external forces, we could apply, after we apply internal forces, we can apply external force. So just with those two lines, now I can add my constructor parameters here and see how it goes. So the way I've built this is joint 0, 1, 2, 3, and 4. So if I want a strong downward force on joint 3, I can do it this way. So what this says is that I have a 100 unit downward force on J3, which is this one right here. So let me go ahead and run bundev. And now when I refresh here, now nothing happens. Oh, and I know why exactly. I never called the struct step function. So if I do struct.step dt over 1000, and then I run that, now we should see, you can tell that some force has been applied to this one. So if I set it to J4 instead, we should see the opposite. So there we go. And I can also set it to, let's say, J1 here. So we'll have some force pulling down here. There we go. So as of now, we actually have a simulation running. I still haven't figured out the issue when you set the stiffness too high. But so far, the simulation seems to be working. You can apply external forces. We have the struct class, or the structure class, that keeps things pretty organized when you're stepping through logic and drawing it to the canvas. We've added mechanical properties. We can pin joints. We've added gravity. We've added damping. So there's actually a lot that we did in this video, but there's still a lot more to come. I'll see you next time, and thanks for watching.